So welcome on this ConSteel webinar about the new functions in ConSteel and csJoint version 9. Let me introduce myself. My name is Szolai. I'm the Technical Director of ConSteel Solutions Limited, and I will make this presentation together with my colleague András Herbai. First, some practical notes about the presentation. You can hide this panel with this red button, and if you would like to ask something, just use the chat area and we will collect all the questions and we will answer it at the end of the presentation. Or during the presentation, if you have something problem with the voice or whatever, then from time to time I try to check the questions. So about the content, new functions of the new version will be presented. There are 3 groups. 2 functions are very unique in ConSteel and not available in other software. This will be a little bit more detailedly presented. The frame corner wizard and an automatic function for stability design. And the first group of the other functions are shown on a simple 2D model. These are the line loads for meteorological loads, plastic hinge analysis, automatic imperfection amplitude will not be shown here, but this is a new function and there is a complete webinar on this topic. So those who are interested, please visit our YouTube channel and you can find a detailed webinar on how to use the imperfections in ConSteel. But this is a new function in ConSteel 9. And the csJoint functionalities will be shown, a new beam-to-column connection, preloaded boards, shear stubbing, base plate, and the foundation design. And my colleague will present new functions on a 3D model, which is the automatic meteorological loads, the surface loads, crane and moving loads, which is one of the major function in ConSteel, influence line calculation, and an automatic documentation of the design results. So first of all, I would like to speak a little bit about the 2 new unique functions, the corner wizard and the automatic stability design. As we will see, I will show how to use it, and I would like to concentrate on why to use it and how to use it in the right way. What problems handled by these functions. First, the corner wizard. If we model our structure by beam elements, line elements, then there are some problems in the modeling, calculation and design. These are collected here. So the theoretical, basically the theoretical connection point, which is here, can be very far from the real connection, which can be either here or here, but not at the connection lines. And this area, this corner area, has a special behavior, both an in-plane, out-of-plane for deformation and for buckling. This is very different from the beam-like behavior. So it is rather like a shear panel, and this is handled in our new function. And the third thing, that the member forces, basically the bending moment, has usually a peak value at the theoretical node here, which is not realistic. So if we want to design our members, we can design it for the member forces acting at the connections. and not at the theoretical node. So these problems are treated in our new function. I will show you how to use it. And the second is the sensitivity-based automatic stability design. What are the problems in a complex structure? If we model a complex structure with all the parts, there are several problems in stability design if we want to use it, if we want to do it efficiently and fast. For example, there are certain questions which are those parts in our model where the stability design is completely negligible or very important. So we have to distinguish those parts. Usually only just some members which are critical from the point of view of stability, and those should be designed carefully, and a majority of the other parts have no stability problem. And how to distinguish? This is the first question. The second, regarding load combinations. The same, if we have very large number of load combinations, which can be dominant for stability design. And finally, if we calculate a lot of failure modes, what are the most relevant for the critical members, which can be the base for any kind of backlink check. So these are quite important questions, and as you may know, we already implemented in ConSteel the sensitivity analysis for stability, which is based on deformation energy classification of the backlink modes, and we are seeking for the critical members in that way, and a mode relevance factor is constructed, and based on these factors we can evaluate the relevancy of each member from the point of view of stability design. And in this new function, this analysis tool is moved forward to design, so fully automatic design can be run based on the sensitivity and backlink analysis. So let me start the first group of new functions to show you on a simple frame model. This is a hinged frame with fixed bases, and I've already made some load cases, wind, snow load, and the necessary combinations. And I would like to show you how can we define quickly the wind and the snow loads, so the meteorological loads on our model, on our 2D model as line loads. The first thing which is different from the earlier versions, that we have to pre-select the members. So first I would like to apply the wind load on this column. So I select the column and I select the line load and the second tab for wind load. The settings are the same as in the older version. So first we have to choose a wind velocity pressure, which can be set here. And if we have chosen this, then we have to choose the internal and external pressure. For this crosswind, we choose now the negative external pressure coefficient, so as to increase the vertical load on the roof. And for external pressure, we have similar dialog as before, but now it is automatically taken to the members. So we have to choose the surface type on which this line member is acting, the wind direction, which is now 0, that means this is a crosswind in this hole, and then what type of area, wall area it is. Now if we consider that the wind direction is from left to right, then it is a front wall. The next, we have to specify the frame distance, it is 6 meters, and then we have the coefficients here. And if I push OK, then we can see here the load intensity, including internal pressure, external pressure, the frame distances as line load, and distributed on a length of a 6 meter column. So it is automatically identified. We have to push this button, place load, and there will be our load. The same convention is valid for the local coordinate system. So the local z-axis should be the direction outward. So in every member, the z is out of the internal area. Okay, we move to the other column. The procedure is the same, but it is not the front wall but back wall. Okay, and place. Sorry, I have selected 2 columns, so only this column. Back wall and place. And here is the load. Okay, and then select the whole roof, including 2 members together. And we change the surface type. This is a dual pitch roof. We have to put the position of our frame as a compared to the whole length of our hole. Let's see that it is somewhere. Oh, sorry. It is somewhere in that area in order to have the highest values from these regions. And then for the frame at that area, so this is maybe the second frame, we have 4 cases for wind load. So we have to choose what case to apply. The first case with a negative coefficient means that this is wind suction, but now we want wind pressure in order to combine it with the snow load. So then we have to choose the 4th case. Okay, and together with this negative internal pressure, we have the load intensities here along these length of our members. And if we push the place button, we can see the different intensities along our members. It is automatically divide the members and take there. So in this way we can very quickly put the wind load even to a 2D structure without using the surface load option. And if we go to the snow load, the procedure is quite the same. Snow load is in the last tab here. These are the parameters of our snow load. We can put simple snow load or exceptional snow load, and what we have to set is the shape factor. In the shape factor we have to put the surface type again. It is a dual pitch roof. The frame distance again 6 meters, and then which is the case. We have now 3 cases: the total snow load or the partial snow load. So the first case is snow total. Okay, we place it, then change to snow left. That means that we have highest value at the left side here. Okay, and then snow right. This is the second case, and we place it. And then we have all the loads: dead load, crosswind, and snow load cases on our structure. So if we want to make any other wind or snow load, we can use these semi-automatic options to increase the speed of loading. Okay, the second task, what I would like to show, is now the plastic hinge analysis. So first, I would like to show you the new analysis parameter table. There are a couple of new functions in the analysis. That's why it is a little bit more complicated as earlier. It is starting with a global setting group of parameters. First, this new combo for the type of calculation, which can be now elastic or plastic. For plastic, we have another settings which I would like to show you a little bit later. Then calculate combination. We can calculate as in the earlier version global imperfection application if we have any kind of imperfection, and inclusion of connection stiffness automatically. The second group is the statical analysis. We have ultimate limit state and serviceability limit states for our second order analysis. And what is new now, that for the second order analysis we can choose a special model portion for which the second order analysis has to be run, and that can avoid us in complex structures where we have bracing elements which can buckle. And in earlier version, in this case, if this buckling is the alpha critical value have a value below 1, then we cannot perform the second order analysis for any kind of model portion. Now it is avoided and solved. So the procedure is same as for buckling analysis. Any kind of specific model portion can be chosen here, and then the second order analysis is solved by compiling the second order matrix, stiffness matrix, only on the selected model portion, and the other portions are left out from the second order effects. Only the first order stiffness is considered. There are options for elastic analysis on load cases, and a special option for foundation design. For foundation design, we need special combinations, and we have to analyze the basic. We have to analyze the load cases with basic values in order to compile the specific combination for foundation design. This is the check for it, and there is a new tool, the elastic analysis of influence graphs. This will be presented later by my colleague. The third and the fourth group is not changed, has not changed. So buckling analysis, sensitivity analysis, and vibration analysis can be run. So let me show you now the plastic analysis of this frame. First, I run an elastic analysis in order to see the behavior of our structure, to see the utilization and the basic buckling forms. So I have some combinations, and now I run the basic analysis types. We can see here the first order, the buckling designs analysis. So we can see the basic buckling forms of our model. It is mainly the beam. In the sensitivity, we can check the relevant part and the relevant alpha critical values. And if we want to see the cross-section utilization first, then what we see is that even for cross-section design, the frame is not adequate at the moment. At the top of the column, the utilization is higher than 100 for the cross-section. Of course, here we have the highest bending moment, and that's why it is not adequate in this way in combination 2. So now, after this, let me show you the plastic hinge analysis, maybe in this most dominant combination 2. Of course, we can run for each combination the plastic hinge. First, I would like to show you the settings for the plastic hinge analysis. This is the setting panel. In the first group, we can set the conditions for the development of this plastic hinge. We can choose a model portion in which the program will seek for plastic hinges, and we can set 2 constraints for the calculation of plastic hinge. So it is seeked only in cross-section with at least one axis symmetry, so monosymmetric cross-sections, and only in cross-sections which are compact, so class 1 cross-section. Basically, these are rules from the Eurocode. So Eurocode allows the plastic analysis using only this type of cross-sections, but maybe if we want to evaluate other cross-section types, we can check out these constraints. And the last thing is on the accuracy of the determination of plastic hinge. The second group is for the behavior of plastic hinges. I would like to say a few words about the plastic hinge calculation in ConSteel at the present version. So it is basically a planar plastic hinge. If we consider the development or the source of the plastic hinge. So we consider only the in-plane major axis bending when we seek for any kind of plastic hinge formation in our model. That means that the effect of any other internal force like minor axis bending or shear or normal force these effects are neglected. Only the major axis bending is considered in the formation of plastic hinge. But after a plastic hinge has formed somewhere in our model, then the behavior can be spatial. So 3-dimensional behavior can be set, which can be very beneficial if we would like to calculate, for example, stability, so buckling analysis on our structure, including the plastic hinges. So this group is regarding to this behavior. We can define plastic rotation about major axis, which is obvious because this is the main plane of our plastic hinge. But 2 other options are available: plastic rotation about the minor axis and plastic warping deformation. Which are these options? So if a plastic hinge has formed somewhere, for example in an I-shaped section, then both of the flanges are in a fully plastic state. That means that the minor axis stiffness has been also lost, and the warping stiffness as well. So if we put these checks, that means that if there is some kind of calculation for which we need at this position some kind of minor axis or warping movement or displacement, then there will be released degree of freedom at that point. So this 3-dimensional spatial behavior of the plastic hinge after formation can be considered. The next group of parameters, or the sets, are warnings. So as I mentioned, only the major axis bending can cause plastic hinge in our model, but we can set warnings to warn the user about the possible relevancy of other sources. So the normal force, if the normal force in any plastic hinge exceeds some limit as a ratio to the plastic resistance, then a warning message came. It is monitored for each plastic hinge. Same for minor axis bending and minor axis shear. For minor axis bending, it is the 10%. For normal force, it is the usual 25%, and for shear force, it is the usual 50% utilization for the plastic resistance. Usually, if we have a plane frame, like in our model, there are no such effects. So in the plastic hinge, these other internal forces are not higher than these limits. So that means that according to the Euro code, these effects shouldn't be taken into account in the plastic resistance of our cross-section. And the rotation in the plastic hinge is also monitored, and if it exceeds a limit specified by the user, then also a warning message come. This limit is there are lots of data in the literature, but usually this 6 degree is enough. And then there can be settings for the deformations and beam for the results which should be saved during the plastic analysis. So if we accept these settings, we can run the analysis. First, let me show you a first order plastic hinge analysis and run the calculation. And what we see here in this combo, a new line, the plastic hinges, and we can see the different stages, what is the load level, and the place of the plastic hinge. So we can see that the first place is at the top of our column now. The second is the top of the other column. The third is the maximum bending moment at this beam. And finally here and here, this is obviously a not relevant plastic hinge just next to this other hinge. And we can see the deformation and the internal force diagram at any stage of our plastic analysis. And in the first order analysis, that means that for load level 1, so at the design load levels, a special analysis is performed, in which all the plastic hinges which formed before the design load level is considered. Now 2 plastic hinges under 1, if we see the stages. These 2 first plastic hinges below 1, and the third and the fourth are upper. So that means that only in the first order analysis, only these 2 hinges are relevant, and this is the stage for which the design can be run. And if we run the design now for the cross sections, what we see that of course we have 100 utilization at the top of our columns. So earlier it was 108. According to elastic analysis, if we consider the plastic reserve on our model, we can utilize this by plastic hinge analysis. Of course, we can somehow be assured that there are no stability problem at this region. For this plastic, the stable length design is can be run, which is at the moment not available in ConSteel, but during the year we will release in an update the stable length design as well. So this was the plastic analysis. There will be a specific webinar on that topic because we implemented the second order plastic analysis as well as the buckling analysis, but due to restricted time now in our webinar, I would like to move on to the next two functions, which are the frame corner and the automatic stability design here. So first, the frame corner. First, how to use this frame corner wizard. Here is a new button in the structure member tab. If we push this button, here are the frame corner wizard main dialog. The use of this function is very simple. Only two things can be set here. The first, if we have model portions like we don't have now in the simple model, but if we have any model portion, we can choose several portions in which this frame corner wizard should be applied. And this is the checkbox which should be checked, and then an automatic recognition is performed for the model with the apply button. So if I push the apply, we can see that all the column members are automatically identified, and all the column member and beam member connections are identified, and basically the covered areas are selected. So this is the area which is the frame corner area. So because we have now a hunch, that's why it is quite high, and in the beam we have this area which are connected to the frame region. So what's happening in the modeling phase? What is obvious from this picture, that the first effect is that the hunch is placed automatically to the right position. So if we don't have this frame area, so we take out this check, then in the earlier version, if we define the dimensions of the hunch, it is measured from, obviously, from the theoretical node of our connection, which is here. This is the theoretical node of our model. But in reality, the connection is here. If it is an end plate connection, for example, is taken to here, so the hunch dimensions should be measured from here, and that is automatically corrected using this function. So the length of the hunch is measured from this point. This is for modeling, and this is same if we have hunch in the column or if we have more connected members here. So this is for modeling. And what is the impact of this applied frame corner in the analysis? To show it, first I run an analysis without an elastic analysis without the application of this frame corner wizard. So I run elastic analysis with first order and buckling. In this second combination, what we see that this is the main buckling mode at the beam, and of course if we see the movement here and from upward, we can see that of course it is moving from the theoretical node as if the connection would be there. So this is the first impact, that if I apply this corner wizard, then it will change the backlink behavior of our member. Now the alpha critical value is 3.97, and if I run the analysis again, then it is a little bit higher now, because it is considered that in this corner this area is not under a beam-like behavior. Practically the software creates two specific finite element here, which is connected to the frame region, and these are neglected from the backlink analysis. So it is the same if we consider a partial model which is not in which this corner area is not included, and the analysis is run without consideration of this frame area. In that case, it modifies basically the behavior, the backlink behavior of the member. It is more realistic because the connection point is taken to the right position. And if we move on and see the global checks, first for the cross section only, and calculate, what we see that the utilization is dropped down significantly. So based on the elastic analysis earlier, the highest utilization was 108, and now it is 92% at the top of our column. What is the reason? The reason, because this frame corner area is automatically neglected from the cross-section calculation. And this is because it is not realistic to calculate bending moment at this region, because this region is not a beam-like behavior, has not a beam-like behavior. It is rather a shear panel which is handled in the connection design, and our members, our cross-sections should be designed for the final cross-section in this below this frame corner area in the column, and in the beam as well beside the frame corner area. And if it is done, since the bending moment diagram, if we see here, is dropping down significantly, we can see that instead of 354, we used the design this value, which is 302, which is significantly lower, almost 20% lower, and that makes a beneficial effect on the utilization of our column member. And it is especially the case if we have large cross sections and the covering corner area is very large. So it has a very good impact on our cross-section design. And if we want to do the stability design, I would like to show you the this frame corner wizard together with the next unique function, the automatic stability based design based on automatic stability design based on the sensitivity analysis. So as I showed you earlier, the sensitivity calculation gives us the relevancy of each member in the backlink mode, and in the summary we saw that the beams are of course the relevant members. Almost all the backlink modes, what we see here, are connected with some kind of lateral torsional backlink of our beam. So the column is not really relevant from the point of view of backlink design. What is the reason? The reason is that we have fixed column base. That means that the bending moment in our column are changing significantly. So here, this is the compressed part, here the other. So this is very beneficial if we look the lateral torsional buckling behavior, and we have an internal support here in the middle of our column. So that's why the column is not really relevant from the point of view of buckling design, and it is clearly it can be clearly seen in the stability sensitivity analysis that for all the buckling cases the beams are relevant. So the beams are red, the mode relevance factor is high for the beams and very low for the columns, we can see. And this result is automatically taken to the global check, global buckling check. If I run now the global buckling check of my simple model, we have a new option here that the elastic critical load factor, which is needed for the calculation of the member slenderness values. Earlier it can be based on the first eigenvalue or a selected one. Now it can be used this automatic function based on the sensitivity analysis, which means that for each member the most relevant buckling mode is applied and the connected alpha critical value is received from the analysis and used for the evaluation of the general method, the general slenderness. And if we run the design, we can see now the stability, it is almost adequate. Of course, our beams are the relevant, and in the column we don't have stability problem. So if we see the column, if we see directly the global stability resistance, we can see that the column is irrelevant from the point of view of buckling, and the relevant structural parts are the beams. There are options for visualization of the inputs for the buckling analysis. If we push this button here, then we can see in each combination the dominant alpha critical value, for which member which alpha critical value is used. So we can see that this 4.06 is used for the beams based on this dominant buckling mode here. And for the beams, they are not relevant. So the beams are not relevant for buckling design. Stability is not evaluated in the column. And we can check the alpha ultimate values, which are the alpha ultimate values in each members, and finally which are the slendernesses of our members, which slenderness values are the base for the calculation of the reduction factor. Of course, it is still not relevant for the columns, and only the beams are evaluated for stability. So it is a very efficient design. Later in a three-dimensional model it will be shown how can it accelerate the stability design of a complex structure where very different buckling modes can be relevant for different parts of and different members of our structural model, and it is automatically identified and efficiently applied in the design phase with this new function. And finally, if we see how this this beam performs without these two new functions, then we can check the difference. So if I take out the frame region wizard, run again the analysis, and use the usual first buckling eigenvalue for the design of the whole frame, calculate it, then we can see that the utilization is significantly higher because of these issues, even in the column and in the beam as well. So even for this very simple frame, we can achieve utilization decrease using these new functions, and these functions are very reliable because we with the frame corner we can consider a much more realistic modeling, and with the automatic stability analysis the mode relevancies are taken directly into account. Okay, the next point will be the csJoint functions. I start with the foundation design, how it is implemented. I should say that the foundation design and the new beam to column connection will be released in our next update. About 2 weeks time we will release it. Okay, so foundation design. We have to start with the special analysis I mentioned. So we have to check this checkbox, elastic analysis of basic values for reactions for foundation checks. So I run again the analysis including these new things, and if we choose the first order we can see the reactions for each load cases which is needed for the foundation design. And then we go back to the structural members tab, and we can use the joint identification tool. So we create a joint by clicking on the column base. Next we choose this rigid connection or the other anyway, and create the joint. We can see the created rigid joint, and what we see here in the left area that we have more options here, and together with the base plate column base connection design we have the foundation design as well. We can see here the foundation types, normal pad foundations with steps and with specific options. We can set here the dimensions of our foundation. We can set the soil layers here with colors and with parameters like saturated weight, dry, humid weight, the angle of friction, and etc. what is needed for all the design. This is in Hungarian, sorry. Maybe I choose another one. Yeah, it is just layer 1, 2, 3. And using these things, the bearing resistance is calculated. I show you later. Maybe I show you how you can create layers. You can use existing layers and push this new soil button. Then a new soil, like soil 2, is created, and then we can modify the layers, anything what we want. For example, this elastic models or whatever. We can include new layer 5 with the thickness of this layer and these parameters could be set. Yes, and okay, I saved. And this is our new layer, and I would like to show you where these layers are taken. If you see the documents and ConSteel folder, there will be a foundation folder, and in the foundation folder you will see all the layers you create. Now this is the earlier layer, and if I save this model, then we will have the new layer as well with saving. Okay, so we have the layers now. We have to specify the level of foundation. Now it is 1 meter below the ground level. We can specify the water table if we have. Now it is here, 3.5 meters below the ground level, and there are design settings for the evaluation of resistances and settlement. First of all, design method should be specified. It can be based on selected national annex, or we can directly select the design approaches which are specified in the Eurocode, this pre-design approach. We can calculate drained or undrained condition. We can specify settlement limit. For the sliding resistance, we can consider passive earthquake, and we can specify here the internal friction between foundation and soil. So these are the basic design settings, and we can specify here the loads on our foundation. Of course, if we have a model, then we can receive all the loads from the model using the placement function. And this is also a new tool in ConSteel that directly after identification of the joint, we can use this place button. So immediately we can place the identified joint geometry back to the global model, clicking here and here. And here are the new joint and joint placement, and immediately see all the results. It is not adequate at the moment, the base plate connection, so we have to improve it. Maybe quickly we can do it by increasing this height. Okay, this, yes, and the wedge should be a little bit larger. Good. And then we can go to the foundation design. In the foundation design, here are all the load combinations which are automatically created based on the values coming from the analysis. So the reactions for the dead load and the live load and dead load and the loads coming from the wind and the snow. All the necessary combination according to the selected design approach for ultimate limit states and serviceability limit states are generated, and the dominant case is automatically shown. It is now the first combination for ULS and the 13th combination for SLS combination, and we can see here all the detailed design. What is calculated now? The bearing capacity below the pad foundation. Here are the detailed design for bearing. The sliding resistance is evaluated and the settlement. If we choose a combination for SLS, then even we can see the settlement values and the design stress values under the foundation. Here we can select a reference soil for the calculation of bearing capacity. The parameters of this soil layer is used to the evaluation of the bearing capacity. There are errors if the eccentricity is too large. So in this case we have to modify the still large the eccentricity, so we have to modify the basement dimensions, and now it is good even in this combination. Of course, if we have high bending moment and quite low vertical load, then we can vary large eccentricity, so we have to increase the width of our foundation. So this is the foundation design. I save it, and I would like to show you directly in the csJoint csJoint model the new functionalities connected to structure connections. So first of all, the new beam to column connection with tension splice. So I make a new connection, beam to column joint, and on the right flange we have now a new option here, moment and plate connection with bolted tension splice. I can choose a cross section for it, okay, and for beam, for column, let's say this, yeah, and I create it. We can see here the arrangement of this new connection type. Basically it is a full strength stiff connection. It can be used efficiently if our beam is fully utilized here and we don't want to apply hinge, but want to have a full strength rigid connection here. Because of the deflections or whatever reason, this tension splice can very efficiently make a stiff connection here. Everything is working like earlier, so all the stiffeners can be set for the connections, flange stiffeners or shear stiffeners. The loading is the same on the beam. Even additional hinge can be set, or the angle can be set. The end plate height should be larger here. And there is one more tool for the tension splice. We can specify here the dimensions and the boards for this tension splice, even more boards, and this is immediately evaluated. Here you can see all the design. It is calculated like we have one compression component similar than the connection method for the moment and plate connection, and all the tensions are taken to the tension splice, and these internal boards are used only for the shear forces, and the tension splice is checked for the boards, for the tension splice area, of course for the welds here, and even the monosymmetric net cross sections are checked here at the end of the beam. So this is the new tension splice connection for rigid connection type. The next, what I would like to show you is the preloaded boards or pretension boards. Pretension boards can be used in splice plate connections. So even if we have splice plate here, or for example in a beam splice connection, I show you now this splice plate beam splice connection. Now let's see this. So this is a classic splice plate beam splice connection, and if we P2 distance, there's this page. Like we have something error in the distance. Okay. Make let's go on the flange maybe. Yeah. Should be larger. Okay, anyway, there were some error because of the geometry check, but I would like to show you that what is the application of these pretension boards. Of course, if we have normal boards, the shear bearing resistance and the tension splice resistance are checked, but we can specify for the splice in the boards, pre-stressed boards. In checking this, there are parameters modifying the check of this type of connections. So regarding the holes, the boards, these are coming from the Eurocode. This KS value is needed for the design, and for the friction between the plates, we can define these categories. If we accept and apply, okay, then we can see that the slip in the flange, we will have the slip resistance calculated for the preloaded force coming from the bolt diameter, and a new value for the flanges can be calculated. Even it is same for the webs, and it can be used for gasket plate connections with I-shaped, with hollow cross sections, so splice gasket plate bracing cross sections, and for the simple splices as well. So this is the preloaded boards, and the final joint main function is the shear stub in the base plate. So let me show you base plate connection with a rather large column. Usually it is used when we have a pinned connection. So now I make pinned connection with only one bolt row, and if I take some normal force and some larger shear force value, then we can see that if we don't want to use a bigger diameter for the bolt, then it is maybe not adequate, the shear utilization, and then we can go to the column, and this is the new function, apply shear stub, and we put this, and the situation is now better. We can see the detailed calculation of the shear stub resistance. What is not adequate now is the compression flange, compression resistance of the flange of the shear stub. So the concrete crashing is checked, the shear is checked, the welds are checked, maybe with the larger length. Now it is fully adequate. So small shear stub can quickly applied, and it will modify the resistance of the shear connection. So these are the basic novelties in csJoint, and now I would like to give the presentation to my colleague András, and he will continue with the three-dimensional models.
Hello everyone, my name is András Herbai, and I'm going to hold the second part of the webinar. My topic is the 3D related functions. I would like to show you the new functions on a 3D hole. You can see the model. This model contains a crane girder, a craneway. The model is fully covered with load transfer surface, and now we have a dead load on the structures. Before I start to show you the new major functionalities of ConSteel 9, I would like to show you a small but very useful new functions. In ConSteel 9, the supports can be placed with a new function. This is with this new function can be used with this black arrow button. The function multiple support can be placed by selecting this black arrow button, and with the selection functions we can place the support on the selected parts of the members. Okay. The next topic is the meteorological load generations. So the meteorological load generation is almost the same like in the earlier ConSteel version wind load generation, but the wind load generation was further developed with a lot of useful tools, and the snow load generation was also implemented. Before we start to generate the meteorological load, as was in the earlier versions, we have to place the surface, the meteorological load surface on the structures on the load transfer surface. So with the meteorological surface, we can select and place the selected surface category. Now here you can see the new meteorological surface dialog. It is divided into two parts. Now we have a wind surface and the snow surface parts of this dialog. With the checkbox, we can uncheck or check the placing surface types. Before I place the surface, I have to set some Eurocode parameters. Let's start with the velocity pressures. With the 3D button, we have to create a velocity pressure functions. To create the functions, we have to select the terrain category. The parameters is automatically loaded from the selected Eurocode national ENA. Now I'm using the EN recommended values. So here you can see the loaded parameters. And the basic wind velocity has to be set, but it's also loaded from the national ENA. Now I'm used for the basic wind velocity the 25 meter per second value. With the OK button, we can create the velocity pressure function. With the 3-dot button, we can set internal pressure for the generation. It's also a new functions in ConSteel 9. We can use an alternative internal pressure factors also in one direction. In the earlier versions of ConSteel, for one direction we can set just one internal pressure coefficient. Now we can set 2 cases for one direction, but I'm now just use just one case for each of wind direction. For the 0, I'm use the plus 0.2. For the 90 direction, I use the minus 0.3 minimum values. For the 180 degree direction, I use the plus 0.2, and from the last time also use the minus 0.3 values. With the OK button, we can create the internal pressure settings. As the new functions in the wind load generations, we can also add the wind friction according to the Eurocode. In the 3-dot button, we can select the roughness of the surface. Here you can see the 3 previously created roughness category according to the Eurocode. And also we can define a we can use a user-defined value also. Now I'm use the very roof because our hole is covered with trapezoid sheeting. Okay, the last parameter is the geometrical parameters. Here we have to set the building dimensions to the basic wind directions. The default basic wind direction is the plus X direction, and here we can set the parallel and the perpendicular dimensions of the building. Okay, the last step is to create the snow load parameters or set the snow load parameters. With the 3-dot buttons, we can set the snow parameters. According to the Eurocode recommended values, we have just one snow load zone, and the value is just one value. It's not the characteristic snow load is not depending of the site altitude. It's just one value, 1.25 kilonewton per square meter. So that's why the site altitude it's not necessary to set. Wind coefficient and the thermal coefficient can be set, but it's also automatically loaded from the selected ENA, and the exceptional snow load coefficient also can be set if it's necessary to generate exceptional snow load also. With the OK button, the snow parameters are also created. Okay, the next step is to place or set the surface categories on the building. From the first drop-down menu, you can select the different surface category. First, I select the wall and place with a left mouse button, just clicking on the load transfer surface, and I'm placing the meteorological load surface on the wall. Here you can see the symbol of the wind surface. Of course, snow surface is not placed on the wall. The last step is to select the dual pitch roof, and with to selection, the dual pitch roof meteorological surface is placed on the roof. Here you can see two symbols show us that also the wind surface and also the snow surface is placed on the structure. Okay. The next step in the meteorological load generation is to generate the loads on the structure. From ConSteel 9, it's not necessary to create previously a load group for the wind and also for the snow load, and to create previously manually also the load cases. It's not necessary because it's automatically created the necessary number of the load cases according to the place, the surface type. So let's click on this button. Here you can see the new meteorological load generation dialog. It is divided to two parts. The first part is the settings for the wind load, and the last part is settings for the snow load. Here you can see the direction of the wind, and in the row you can see the different the placed wind surfaces and the internal pressure and then the wind friction. If you would like to generate internal pressure with the checkbox, we can switch on, and also the wind friction can be switched on with the checkbox. Now I uncheck the 180 and the 270 direction because our hole is double symmetric, so it's not necessary to generate, just to make faster the calculation. Okay, here we can see in the snow load area, snow load field, we have one snow surface, and it will be generated because the checkbox is checked. With the OK button, the snow and the wind load is automatically generated. Here you can see the wind load groups and the snow load groups is automatically created, and the necessary number of load cases in the different direction is automatically created, and also in case of snow loads, it's also the necessary number of load cases is created automatically. Let's see the created loads. The green arrows show us the direction of the wind, and here we can see the different fields of the wind loads, and we can see in the property area the velocity pressure and the calculated load intensity, and also on the sidewall you can see the A and B zones. C is not created because the dimension of the hole is not big enough, and also the wind friction is also not created because the size of the length of the parallel length of the hole is not large enough. You can see in the other load cases also, and here is the perpendicular wind load. In this case we have just one load cases without internal pressure and one with internal pressure. The snow load also can be seen in this case. In case of snow load we have three different load cases, one total load and two half load. Okay, so this is the new meteorological generation in ConSteel 9. The next topic is the moving load and the crane load. It's not just one function. It is a function group. Here you can see this function group contains influence line function, the influence graph function, crane load function, and the moving load and terrain load functions. Before I create a crane load, I have to place on the model an influence line. Influence line can be draw or can be select. It can be also a double influence line. For example, in this case, I would like to place on this model a crane load. Now I'm using the double influence line and the selection options. Just select the beam, and with the right click I can continue the selection. Okay, and if the influence line is created, a yellow line is show us where is the influence line is placed. Okay. Next step is the crane load. To create a crane load, we have three types of crane load. We have a standard. It is fully Eurocode based crane load creation. We have another type of crane load. Is the standard load based crane load type. In this case, just the number of the axis has to be set, and the different Eurocode wheel loads can be given or set in each of in case of each of wheels, and also the wheel load is automatically and the load cases is automatically combined and created by ConSteel according to these dynamic factors, which is they are also loads automatically from the Eurocode selected Eurocode national ENA. But if it's necessary, but these dynamic factors is just the minimum according to the Eurocode. If it's necessary, it can be modified manually. And also we have a user-defined crane load. In this case, number of the axis has to be set, and the wheel loads in the three different directions can be given. Now I'm showing you the standard type of crane load. We have to set the span of the crane bridge. Now in this case it is 21.3 millimeters. Minimum distance of the trolley. This is the minimum distance. Now it is just 0. Now I'm select 4 axes, and the distance between the axes is 1.2, 1.0, and also 1.2 meter. Okay. The next step is to set the self-weight of the crane bridge. It is 70 kilonewton. Self-weight of the trolley is 15 kilonewton, and the elevated weight is 180 kilonewton. Now I'm used the default dynamic factors for the creation of the load cases. Number of the single wheel drives also can be set. Now I'm used on default, it's 2, and the wheel drive type can be set, it's central or individual. A crane system also can be set according to the Eurocode. I'm used, and the first one is the CFF crane system type. Friction factor between the wheel and between the rail can be set also, and the guiding device type can be set. We can use the flanged wheel also, or the guide pin. Now I'm use the flange wheel, and I leave on default these 2 parameters. And on the last table you can see the automatically calculated wheel loads in the 3 different directions, and from the drop-down menu you can see all of the Eurocode defined crane load cases. Crane load can be placed on the model in 2 ways. The first way is to place manually with this place load button. In this case, you can place manually the selected load cases in the selected load cases. Just click on the part of the structure, and with this selection or with this settings, okay, so the selected crane load cases can be placed on the influence line manually. So this is the first way, but crane load also can be placed on model by loading on an influence graph. To analyze an influence graph, we have to create some influence graph settings. The first parameter, we have to select the influence line. Now we have just one influence line, it's a double influence line, so that's why we have to choose just this first one. The next step is to select the cross section. influence graph. Now I'm select the middle of the first bay of the crane girder. Just click, and the next next setting is the type of the influence graph. We have three different influence graph in this version. The first one is the displacement. The second one is the beam force or internal force influence graph. The last one is the reaction force influence graph, but it is available when I select a point where a point support is placed previously. So now I'm use a beam force influence graph, and here you can see the beam force. Now I use a bending moment, and the direction of the unit load also can be selected in the local coordinate system of the beam. Now I'm select the -z. With the apply, we can create influence graph settings, but with the new button we can create another one. Several number of influence graph can be created and can be calculated. For the second influence graph, I select this point of the beam. The type of the influence graph is still beam force, bending moment. The direction of the unit load is it's okay, the -z. The apply button, I create the influence graph. If you go to the analysis tab and the analysis parameter, we can run an elastic analysis of influence graphs with the calculation button. Okay. So this symbol is show us the selected cross sections, and here you can see the influence graph along the member. And another one, here you can see the section is sphere, and here you can see the influence graph on the crane beam. With the right click mouse button, with this menu we can load the influence line with the selected crane load or moving load. Now we have just one crane load, so that's why it's automatically loaded. The load group can be selected manually, which you would like to use, or can be selected automatically by ConSteel, and also the position of the maximum wheel load can be on the left pass or on the right pass, but it also can be selected automatically. And the influence graph can be loading on the negative zone or also on the positive zone with the moving load. Now I'm select the loading load on the negative zone, and the position of the crane load also, can be saved to one of the previously created load case. But with the 3-dot button, also new load cases can be created. With the save button, we can save this. Crane load position. We can load the other influence graph also with our crane load on the positive zone and also on the negative zone. Now I'm selecting the second crane load case, and I save to the negative zone loadings to this crane load case with the save button. And if you go to the go back to the load stub, you can see the load, the crane load is saved to the previously created crane loads. Because I would like to make faster the analysis, I previously select the dominant load cases, so that's why I will run the calculation just for the dominant load cases. You can see we have huge amount of load combinations because we have wind load, snow load, and also crane loads on this model. Now I calculate first order analysis, second order backlink analysis for the whole model, and the backlink sensitivity analysis. For the selected dominant load combinations. Okay, now analysis is ready. Let's go forward to the global check and run the cross-section check and the backlink check for the first with the first backlink eigenvalue, and calculate the utilization of the whole structure. Okay, so now we can see the utilization of our structure. In the graphical area we can see, and also in the table results you can see that the utilization is higher in case of lot of members of the whole than 100%. So this structure is not adequate. Now the dominant examination is the global stability resistance in most of the members, but we use to check the backlink of the to run the backlink check the first backlink eigenvalues. Let's go back to the analysis tab and let's see the backlink result. Let's see the first backlink shape of the structure. So now here you can see the first backlink shape in the first load combination is the buckle of the compressed part of the bracing system. So this kind of backlink shape and this backlink eigenvalue is not proper for the whole structure. Is proper just to calculate the backlink check of the bracing system or the compressed members of the basic system. Let's see the next one. This is same. In the third combination, the first backlink shape is the buckle of the compressed flange of the truss of the truss. It's also not proper to calculate to calculate the backlink, the stability of the beam and also the column. Here you can see the next backlink shapes. So this kind of backlink shape is proper to calculate the backlink check of the end wall columns. So now, if you like to calculate the global stability resistance in efficient way for this 3D hole, it is necessary to select the automatic elastic critical factor selection based on the sensitivity analysis. And if you use this kind of new functions and calculate again the utilization of the of the 3D hole, you can see the utilization is much more lower. It's almost adequate. Just we have two members, two end wall column, what are not adequate. And if you see the sensitivity analysis and the summary result, here we can see which load combinations and which alpha critical factors are used for each of the members. For example, for this member, for the columns, ConSteel use these load combinations and the second backlink eigenshapes, and also we can see these backlink shapes. Here you can see. So this is the backlink shape which is used to calculate, for example, the backlink of and the stability of the main columns of our hole instead of the first backlink shapes, which is this one. Okay. So our last topic in this webinar is the new documentation functions. So if we are ready with the analysis and the standard checks of our structures, the last step is to create documentations. In the previous or earlier versions of ConSteel, to document the standard checks of our structure is not was automatical. And with manually we can add, for example, this kind of tables to the documentations, and maybe section checks can be section documentations from the section modules can be add to the main document as a as an annex. But now, from now in ConSteel 9, it can be created automatically. If you create a new documentations, in the documentation tree, you can see the standard design is automatically added. This standard design chapter will be added automatically. Now just the ultimate limit state design is available because serviceability checks was not run previously. But if we have a serviceability checks also, the standard design is also contains the serviceability checks documentations. So we have two types of ultimate limit state design documentation. The first one is a summary. The summary is a kind of table. It contains the number of the element, the dominant load combinations, the dominant examinations, and also the utilizations. And we have a detailed results of standard checks by members. To reduce the size of the documentations, utilization limits can be set for this for these tables and for these documentations. In case of summary, we have two kind of table. Sorry, it is one table, but it can be ordered in two way. So it can be ordered by the name of the member, or by the name of or by the utilization value, and all of the members which utilization is lower than the set utilization limit will be skipped from the documentation. So now the minimum is 10% for the summary, and 90% for the detailed result. And now I will just create the utilization, the summary summary table, summary documentation order by the utilization value, and with the create button, the document will be created. And in the last chapter, we can see the automatically created standard design documentation. Here you can see the summary of the standard check by members, ordered by utilization because it was selected previously. So here you can see the number, the bar, name of the bar member, the element where the highest utilization can be found along the member, the dominant load combination, the dominant global, the dominant examinations, and also the highest utilizations. Okay. And if you go to the detailed result, for each member, for ConSteel is create this kind of detailed result for each members. This kind of documentation is contained, and the name of the members, the place of the dominant cross section from the start point along the member, the dominant load combinations, the dominant internal forces, the section parameters, the material of the section, and the use, of course, the use design code. And here you can see the summary result, and here you can see the detailed result, all of the created or of the used Eurocode examinations, and here you can see the utilizations and the applied part of the standard. So this is the new functions in the documentation module. We have other small functions in the documentation module. The page of the documentation can be fit with width of the page, or can be fit with the height of the page. So okay, for now I'm done with my presentation. So if you don't have any questions. I would like to thank you for your attention. I hope you enjoyed and learn in this webinar. And thank you very much. And goodbye, and see you in our next webinar. Thank you again. Bye.